All right, let's just dive right into this explainer. Today, we're looking at something that honestly sounds a bit like science fiction. We're going to explore how we can use abstract software architecture models to solve complex, real-world geopolitical deadlocks. Seriously, independent researcher Osamu Okumura has proposed this incredibly fascinating structured way to map out international conflicts. And the kicker? He's using the exact same tools that software engineers use to build resilient computer systems. We're talking about viewing diplomacy not as this messy, unpredictable shouting match, but as a precise, structured system of code. Code that can literally be debugged. So, to really grasp the core problem here, we first need to define something called meta rules. This concept creates what researchers refer to as a self-referential maze. Think about it like this. Imagine you're stuck in a maze, desperately trying to find the exit. But every single time you take a step, you, or maybe the person you're negotiating with, literally moves the walls. That's what happens in diplomacy. Parties don't just argue over the rules of a treaty, they actually argue over how to interpret those rules. They're rewriting the underlying criteria, the meta rules, while the negotiation is actively happening. And you can probably guess the result. It traps both sides in this incredibly unpredictable, infinite loop. Which brings us to a really fascinating dilemma. I mean, how do we prevent a system from completely breaking down when the rules of the game are literally changing while you're playing it? Because if neither side can even agree on the basic shape of the maze, well, no algorithm and certainly no diplomat is ever going to find a path out. Here is our roadmap for the explainer today. We'll start with the self-referential maze, then move on to the 2026 Hormuz crisis, map the frictions using C4, dive into controlling the chaos with Landgraph, and finally, look at architecture over improvisation. Let's get into it. Starting with Section 1, the self-referential maze. We're going to see exactly how dynamic changes to these meta rules cause negotiations to just nosedive right into an endless loop of retaliation. Moving to Section 2, the 2026 Hormuz crisis. To ground this clinically, we're going to examine the internal workings of a hypothetical 2026 U.S.-Iran Strait of Hormuz dispute over transit conditions. And I want to be really clear here. We're looking at this strictly as a structural systems failure. We are absolutely not here to assign blame or make any political or moral judgments. We just want to look at the raw mechanics of how an agreement breaks down. All right, let's look at the timeline and see how this builds from a static agreement into this escalating, purely reactive loop. In June 2026, a baseline is established, right? A zero-fee framework for maritime transit. Simple enough. But look at what happens just days later. Disruptions occur, tensions start to spike. And by early July, one side basically declares the agreement ended and introduces a brand new meta rule, a 20% transit fee. Now, this isn't just breaking a rule, it's a total rewrite of how the rule is interpreted. So mid-July hits, international legal doubts are raised, and by late July, the other side responds by suggesting their own counter-fee policy. By the end of July, it's a total withdrawal and a scramble for an alternative framework. Both sides just kept rewriting the interpretation of the treaty in real time. It's a classic retaliatory feedback loop. Which brings us to Section 3, C4, mapping the frictions. So to fix this massive structural deadlock, Okumura proposes applying the C4 software model to actually separate those static, foundational rules from the messy, dynamic variables. This completely brilliant concept shows how we can isolate the unbreakable core treaty on the outside from the fluctuating daily negotiations happening on the inside. If you're familiar with software engineering, you know the C4 model breaks systems down into context, containers, components, and code. Applying this to geopolitics, we take the absolute core agreement, something like no transit fees, and place it firmly in the context layer. It becomes this immutable outer vault, completely unshakable. Then, all the daily political posturing, the changing demands, the dynamic interpretations, all of that is restricted strictly to the chaotic, bustling inner container and component layers. The absolute genius of this design is that we can now clearly monitor the boundary between these two distinct layers. Which leads us perfectly into Section 4, Landgraph, controlling the chaos. Because, it's one thing to draw a nice map, but it's an entirely different thing to build a machine that actually enforces it. And we can do exactly that using a Python-based state machine framework called Landgraph. By utilizing conditional edges within Landgraph, we can actually implement a strict three-step procedure. This controls the state transitions and, crucially, prevents our maze from constantly shifting. Think of it as the underlying software logic that just continuously monitors the negotiation room. If someone tries to move a wall in the maze, this logic is designed to catch it instantly. So step 1 is the immutable lock. This means the core agreement is hard-coded and entirely shielded from any dynamic reinterpretation during the heat of a dispute. Going back to our hypothetical 2026 Hormuz example, the rule no transit fees is literally hard-coded into the state machine. It is completely off limits to those dynamic, day-to-day negotiation containers. No touch in the vault. Step 2 is the validation gate. This is where it gets really cool. If the system detects a new demand that's trying to breach that lock, the validation gate forces an automatic rollback to the last stable state. So what's absolutely critical here is that when that 20% fee was suddenly proposed in July 2026, a system designed like this would immediately flag it as a boundary violation. The state machine simply rejects the input. It rolls the negotiation back to the prior stable condition. The system literally refuses to compute the new rule-breaking reality. Just nope, not happening. And finally, step 3, the arbitration node. If the negotiations fall into a retaliatory loop that hits a specific threshold, control is automatically stripped away and escalated to a human-in-the-loop intervention. Because, let's face it, we know human behavior isn't perfectly clean. The code actually tracks how many times the meta rules are challenged. If the parties are just endlessly shouting unacceptable demands at each other, triggering that validation gate over and over again, the system recognizes a deadlock. It flips a switch, handing the unresolved conflict over to a designated arbitration node, say, a panel of international experts, to finally break the cycle. All right, our final section, number 5. Architecture over improvisation. The absolute core takeaway here is that we have to shift our approach to diplomacy. We need to move away from these on-the-fly improvisational reactions and move toward pre-designed, resilient architecture. We literally need to stop fighting fires and start designing fireproof buildings. Now, Okumura is very clear about the caveats here. We have to remember, this model is a structural tool. It is not a political or moral judgment. And actually implementing it, well, that requires prior explicit political consent from both sides. It's not a magic wand, right? You can't just write some Python code and automatically force two nations to agree. Deciding what actually goes into that immutable lock relies on highly political initial agreements based on the power dynamics of the countries involved. Plus, switching over to an arbitration node requires the mutual consent of both parties beforehand. The code doesn't magically create peace, it simply enforces the structural integrity of the peace they've already agreed to build. It's a really powerful idea that completely reframes how we view human conflict resolution. Just look at this quote: "Negotiations should not be a maze explored on the fly, but an architecture designed in advance." If we construct the architecture properly from day one, we don't have to panic when tensions inevitably rise. We just let the system process the inputs according to the rules. So as we wrap up this explainer, I really want to leave you with this thought. If we can conceptually map a complex naval crisis using Python, what other seemingly unsolvable human conflicts could be fixed by treating them as lines of code? Could we use these state machines for climate change treaties, huge global trade agreements? The potential to transform our most chaotic arguments into structured, solvable systems is just absolutely massive. Think about it. Thanks for joining me on this deep dive, and keep looking for the underlying architecture in the chaos around you.